All right, so we're live now with the new microphone. Yeah, the other one broke, so I wonder what this one sounds like. We'll see on the playback. Okay, so we're probably going to test this Thursday, by the way, FYI, just to make you excited. That's an even day, and we're going to test. Oh no, it'll be through 5.5, which is applications to sinusoids, and so your free response question will be like one of these that we are in the middle of, the Ferris wheel problem. Okay. So yeah, it'll be fun. We'll do it together. We'll be there together. I'll be right there as you're taking the test, looking over you, making you nervous. Anyone look outside their window this weekend and see me in the bushes, ready to? Yeah, there you go. I was there, ready to answer any question you had. All right. So just to remind you, we were looking at the Ferris wheels, the Canal County Fair, went up to 105, went down to 5. We came up with this graph. We knew that there was a 3-minute ride, and it took, this was important, it took 6 revolutions, or it did 6 revolutions per minute. That came out to be 10 seconds for the period. Remember, the reciprocal of the angular velocity is the period. We just had to convert it to seconds, okay? So 10 seconds per 1 revolution, that is exactly what the period is. Number of seconds or time for 1 revolution. So we got these points here. And we started at a low point, so we wrote an equation, and we were using it, right? So we finished part D, but now we're on part E, okay? And if you remember, I said during the 3-minute ride, I still didn't change it, during the 3-minty ride, that's what it was. During the 3-minty ride, for how many seconds was the rider above 100 feet? Show the work that leads to your answer. During the 3-minute ride. Okay, so here's what we need to do first of all. Part E. Part E. We need to set the height equation equal to what? We want to know for how long we were above what? 100. Now you could say greater than 100 if you want to solve it like an inequality. I'm not going to be too picky about that. But once I set it equal to 100, here's what I can do. And I have to stay over here because my calculator's over here. If we go to y equals, that's not the equation. I have to type it in again. So very quickly, let me type in, make sure you're in radian mode, negative 50 cosine of pi divided by x instead of t. I'm sorry, pi divided by 5. Sorry, and then times x. And then we close that, and then plus 55. Our window, of course, went from 0 to, we went out to 25. Our x scale doesn't really matter. Our y min, I put -1, and then our y max, so I'm going to go to like 120. Scale to 0. All right, so here it is again. There's what we have. Now that we set it equal to 100, let's graph 100. Remember, when you're given an output, a y value, you set it equal to, and there it is. So we can actually now see the blue part of the graph where he's above 100, right? So if I could figure out the duration of time it is between this point of intersection and this point of intersection, would that be the same duration of time for each of these cycles as well? Yes. So if I can figure out one of them, then all I have to do is figure out how many times he was above 100, okay? So let's do that. Let's figure out this first one here. Second trace number what? 5, right? Intersection. Is this the first curve? Yeah. Is this the second curve? Hit enter? Yeah. Now for the guess, I'm going to scroll. It's easier to scroll in the straight line. So there it is. I'm pretty close to that one. I'll hit enter. It's 4.282. So on my iPad paper, I'm going to write t equals 4.282. Now here's the thing. I've mentioned this before. You never, ever, ever, ever want to use a rounded number for a subsequent calculation. So I need to store that number. So if we go back to the home screen, second mode, if you hit X, enter, there it is. It automatically stores it as X. But we're about to find another one. So I need to store this as something else because it'll always overwrite X. So just hit the stow button on the left, right above on, and hit alpha A. A is right below the alpha button. Okay? You hit enter, and boom, now it's locked in as A. It'll always be A. It never overwrites unless we do it ourselves. Okay? Now we do the same thing for the next point of intersection. So we go back to the calculator's graphing screen, and we hit second trace number 5, enter, enter, and now we scroll a little bit more to the right so we don't find the same one again, although you could do that. 5.717. So I'm going to write that one down. T equals 5.717. And again, I'm going to need to use that number, right? So I'm going to store that as, let's see, go back to the home screen. If you want to hit X again, notice it's different now. Good thing we stored the other one as A. Let's store this one as B, alpha B. Okay, so hit alpha apps, enter, and there it is. Now here's another thing you could do. On your paper, when you write them down, I need to see what the numbers are. So what you probably want to do, let me rewrite it like this. Here are the two T values. If I stored the top one as A, just call it capital A on your paper. If I stored the bottom one as B, call it B on your paper. Not only is that a reminder that you stored them under a certain variable, but when you set up your calculations, you can use A and B, as long as it's an intermediate calculation. All right, so what do we need to do with those? We need to find their difference now, don't we? So, another transitional word, B minus A. That's all you have to write. Equals B minus A. So if I then go to the home screen and do alpha B minus alpha A, it'll give me the difference of the stored values, which is 1.435. Again, we want to write 3 decimals down to report it, and I'll put seconds. But now I'm probably going to have to use that number again, right? Because that's just once around the Ferris wheel. So let's store that one now. What's left open? If you just hit stow, it'll take the previous answer. And let's store it as C, or whatever you want. That's alpha program. I'm going to hit enter. And then I'm going to go back to my iPad and call that C for chocolate. Okay? Okay, so now what? Now I know for once around the Ferris wheel, he spends a little less than 1.5 seconds above 100 feet. I want to know how long he does it for the entire 3-minute ride. So what can I do? I need to figure out how many times the Ferris wheel goes around in 3 minutes. We could do that one of 2 ways. We can go back up here and realize it makes how many rotations every minute? Did it say that? 6 rotations every minute. So in a 3-minute ride, it should be how many? 18? Okay, we could do it that way. We could trust our math, or you have a calculator, right? If you want, I'm not saying this is necessarily how I would do it, you could set your X max to how many seconds is 3 minutes? 180? Yeah, oops, not 280. Sorry, 180. And then hit graph. And there's the ride, there's the ride, there's the ride, there's the ride. And then all you have to do is count. Count how many peaks you see above the red. Ready? Let's do it together. 1 many, many, 2 many, many, 3, 4, 5, 6, 7, 8, 9, pause, 10, 11, 12, reset the mouse, 13, 14, 15, 16, 17, 18. We did it. We did it. We did it. Yeah. We graphed the sinusoid and counted the peaks. Yeah, we did it. We did it. We did it. Yeah. Lo hicimos. It's like a Doors episode, right? Counting the number of peaks. We did it. Lo hicimos. All right, so 18, right? So 2 different ways to get 18. Counting was kind of fun, but the math kind of speeds things up, right? So what do we do with our value now? If C is once around, so the total time, let's just write a little sentence here because we don't want to just put so all the time. So the total time above 100 feet is 18C. You can write that, which equals, okay? And now we'll go back to the home screen. Because the previous number is C, we maybe didn't have to store it. So if you just want to hit answer times 18, but I'm just going to type in 18C. 18C, and we get that. So 25.841 or 25.842 seconds, okay? Now, it's important that you store those values because on a test, like your free response on Thursday, I'm going to ask this type of question because it's a wonderful question. If you're off in any of the decimals, if you get 25.840 or 25.843, it's going to be wrong. Yeah, it's going to be wrong. It has to be correct to 3 decimals. So when do we use a rounded or truncated number for a subsequent calculation? Never. Never. You have entire alphabet on your calculator, A through Z, X probably, so one less, but you can store values. And of course, once you store them on your calculator, write it on your paper so that you remember what it is. Okay, cool. So that's not bad. You give like 10 tickets or whatever, unless you have a wristband, and you spend almost half of a minute above 100 feet. That's exhilarating, right? Yeah. Okay, questions on that one? How we do that one? Fun, 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 fun. Okay, A, B, C, D, E, F is next. All right, this is the good one. This is the one where you're going to really appreciate how much fun you're having above 100 feet. What is the linear velocity of the rider in miles per hour as the Ferris wheel rotates? Okay, what is this linear velocity? Well, linear velocity is in a straight line, right? That's why we call it linear. But of course, we know that we could take that and we can wrap it around in a circle, and we can have linear velocity in a circular path. So we've already studied that. So what is the formula for the linear velocity v for a rotating object? Does it have anything to do with how fast we're spinning? You're on the merry-go-round, you're on the Ferris wheel. Yeah, it does. Okay? And where do you get the biggest exhilaration? Standing right in the middle of the merry-go-round or on the edge? On the edge, right? So it's directly proportional to the radius. The bigger the radius, remember, the larger circumference you have to cover in the same amount of time as someone who's closer to the center, because it rotates at the same angular velocity. So there's the formula, V equals R omega. Let's see if we have enough to plug in. We want to know the rider's linear velocity. So do we know the radius of the Ferris wheel? How can we get the radius of the Ferris wheel from this graph? I think we already talked about it. Yeah, it's 50, right? It's your amplitude. Your amplitude is your radius, okay? So that's 50. I'm going to put units here because we want it in what units at the end? Miles per hour. So the radius of the Ferris wheel is 50 feet, and we're going to multiply it by our angular velocity. What's the angular velocity? Remember, it was given in the beginning to be 6 revolutions per 1 minute. Yeah. Now, if you look at the units, we have feet revolutions per minute. Is that what we want? No, we want miles per hour. So guess what we get to do now? Conversion, stoichiometry, dimensional analysis, whatever. So multiplying by equivalent factors to 1, or factors equivalent to 1. So we'll put feet over 1. Let's do the feet first, okay? So we have feet down here to divide out, and we want miles up here. And what's the conversion still? 1 mile is 5280 feet. Good. Divide out the feet. Now we're left with revolutions miles per minute. Let's do the time next, I guess. Minutes up here, and we want hours to appear. What's the conversion factor? 60 over 1. Good. And now your minutes divide out. And so now we're left with miles per hour, but we have revolutions, miles revolutions per hour. That's no good. How do I get rid of the revolution unit? Convert it to radians. Excellent. I love it when y'all learn things. All right, so revolutions down here. Remember, I'm going to write rad as a description, and what's the conversion factor? 1 revolution is how many radians? Not pi. 2 pi, right? Did he say 2 pi? Oh, okay. 2 pi. Sorry, I didn't hear it, Jojo. But you're the man today, so if you would have said pi, I would have put it down anyway. All right? But then if we put pi radians, we'd have to go over a half revolution. Okay, we could fix it. But you're right, 2 pi radians. Okay, so now revolutions divide out, and we're left with miles radians per hour, which is really miles per hour. We've got it. We've got it. We've got it. Yeah. Okay, I'm not going to sing anymore. Go to the calculator, Medora, flush, and here we go. 50 times 6 divided by 5,280 times 60 times 2 pi, or times 2 times pi, like that. We don't need to worry about the ones. We check it, double check it, it looks good, and voila, there we are. Oh my gosh, 21.419, or if you want to make it like sound like you were really going fast, 21.420. Yeah, here is maybe where I would round, because it's a little more impressive, right? It's a bigger number. So either one of those, and then we'll just put MPH, MPH. So if this Ferris wheel was like in Landa Park, you'd get a speeding ticket because you're going more than 20. Yeah. Good thing it's at the fairgrounds, right? So there you go. Imagine being above 100 feet for about a half of a minute, going almost 21.5 miles per hour along a curved path. And I think now you have your new favorite ride at the Comal County Fair, right? Yeah. It's also good because 3 minutes, that's a lot of time to smooch, right? When you get on with your date, right? Okay. How do you like that problem? Pretty good, huh? A lot of variety in there, combines a lot of skills that we've been learning all year long. It's one of my favorites, okay? Any questions on example 1? All right. Example 2, moving right along. If the rider from example 1, y'all remember him? Yeah, that wasn't too long ago, okay? If the rider from example 1 started his stopwatch when he was 12 feet in the air going up, stupid idiot. He gets in, he's there to collect data, the ride starts and he forgets to start his stopwatch. That's why he's riding it, to collect data. So he started it late. He started it when he was 12 feet in the air going up, we'll say for the first time. What would the new equation be? Could we still use the same equation? No, because this gives his height at any given time. So now, if you say he was 12 feet in the air, 12 feet might be right here. Here's 12 feet. This is where the idiot started it, right? So that needs to now correspond with t equals what? Hopefully he reset his stopwatch to 0. That needs to be my new 0. I can still use the graph, right? Because the sinusoid is what it is. It's still a 10-second period. I just need to do what with that graph to make 0 line up with that point? It rhymes with drift and starts with sh, shift, or translate. I need to shift that graph so that that's 0. Which way am I going to shift that graph, left or right? I need to shift that graph right? Left. Right, left. We're just marching. We're marching. Left, right, left, right, left, right, right, left. Very good. Left is right. You are right when you say left. Left is correct. Right, left, right. Okay, how are we going to find that point? How are we going to find that point? We know it's 12 feet in the air, but we don't know the time. How can we find that value if we know the y value? Graph it. There you go. Okay, so here's what we're going to do. We're going to take our equation from above, h of t, and we're going to set it equal to 12. Okay, set it equal to 12. So come back up here. Y equals, get rid of the 100, right? See 100, 12. And graph. Whoa, hit on. We don't need that many. Let's go back to putting it at 25. Whoa. That'd be cool if it really rotated that fast, huh? Okay. There it is. That's what we want. That's what we want. Second trace, number what? 5. Enter. Enter. Can I hit enter again? Not yet. I got to scroll over here. You can scroll before you hit enter too, but you can always, whoa, now I'm going in negative land. Bless you. It would have been so much easier if we just would have hired a competent guy to start his watch at 0. But nope, now we got to fix it. His mess. Enter. 0.852. Okay, so underneath h of t equals 12, we're going to put that number, t equals 0.852. Now, he didn't start it at the bottom, but notice he did start it within 1 second of the ride moving, so not bad reflexes for a guy who forgets, right? Not bad. Okay, so now I need to, I'm going to store that number just in case. Okay, I'm going to hit X, and I'm going to store it as, D for donut. How about that? Yeah, that's right below man. So we had chocolate, now we have donut. Okay, so on my iPad, I'm going to store that as D for donut. But I'm going to report 3 decimals. Okay, so now come back up here to this equation, our original one. Okay, remember we wrote one in terms of sign as well, and you could use that one if you wanted as well. But I'm just going to take the original one. And now the only thing I need to do is modify it by shifting it over. Okay? By shifting it over. Let me get rid of that t. So it's going to be what? T. If I need to shift the graph to the left, y'all said, right? Left, right? Is it going to be plus or minus? Plus, minus, minus, plus. 0.852. Close, close. Is there any way to check? If we think that should be minus instead of plus right here, is there any way to check? Graph it, yeah. So now, let's go back to y equals. We don't need to graph 12 anymore. So we can just delete it or turn it off. And I'm going to come back up here. And I'm going to put an open parentheses. And I'm going to say x plus. Now guess what I'm going to put? I'm not going to put 0.852. Guess what I'm going to put? Alpha D, alpha donut, right? Because if we wanted to use this equation to calculate where it is, we don't want rounding error. That is way too many parentheses, though. Let me delete one. Yeah, one too many. Good. Plus 5. Okay. Now, if I hit graph, the y-intercept should be 12. Let's see. Trace, and then type in a 0. Remember, when you're in trace mode, it doesn't look like it, but you could type something in. Hit 0 and what does the y value say? 12. Did we shift it the correct way? Yeah. Yeah. Now, just, let's just explore it. I did hear someone say minus. Speaking of minus, this week is Rachel's challenge day, this Wednesday, so we can get positive again. If you put minus D, look what happens. Trace 0, we're at 12 feet. Uh-oh. But we're going down. Very good. Very good. He has to be at 12 feet going up. So we did shift it correctly when we had the plus in there. So when you have your calculator, make sure that you're using it as a tool. We always want to report actual numbers in our final answer, but we never want to use those rounded or truncated numbers for any subsequent calculation. Okay? There you go. So not a big deal. We fixed the guy's problem. And we could look at that problem in any other way. If I said he didn't start at that time, he started it when he was like 70 feet coming down. 70 feet coming down, that would have been about right here. We would have just graphed 70 and shifted it to the left. So that was kind of an arbitrary time. All right, so that makes a good, really, instead of example 2, that could have just been part G on example 1. In other words, that makes a good addition to a free response question. Okay? Yeah, good stuff. Lots of good stuff. It's all good stuff, right? Okay, how much time we got? 20 minutes? Yeah. All right, we need a quick break. Stand up. Bathroom break, get some water. Grab another dodo. Dodo Jojo. Jojo Dodo. We call donuts dodos in my house. I don't know why. I think I started it when my kids were little. You want a dodo? And then they mispronounce it doo-doo. And then, like, man, it's gross. But anyway. Okay, good break. Good break. Clam chowder day. All right, so here we are in example 3. The writer from example 1 and example 2. It's the same guy. It's not two people. Leaves the fair. That guy leaves the fair and he goes home. That's what you're supposed to do, right? Especially if you leave the fair at close to midnight. Nothing good goes on after midnight. Go home. Okay, what does he do when he gets home? He doesn't go to sleep. No, he constructs a perpetual motion machine. Dude, how did he do that? I know, perpetual motion. I don't know how he did it. He didn't give the instructions, but it says shown at right. This is what he built. He had a floor in his house, and he had a hangman's gallows, but he put a spring with a weight on it instead. And I don't know, perpetual motion, you know, because of gravity and air resistance, that's kind of an ideal scenario. So we'll just kind of go along with the ideal scenario. Maybe his room is in a vacuum, you know. Yeah. Climbs into the Dyson, you know, big Dyson. I don't know, not vacuum cleaner, but in a vacuum, like a bell jar. Maybe he's a bubble boy. Anyway, here's what it is. So notice there's a spring, and it's hard to see, but this is 60 centimeters, and this is 40 centimeters. So it has kind of a little dotted line, if you can kind of see it. So this is, it's hard to see on the screen. But there's a basically, if we keep reading, it's going to oscillate perpetually, forever, between a high point of 60 centimeters from the floor and 40 centimeters from the floor. Just back and forth. That spring is going to keep going back and forth. So as it bounces, it's going to vary sinusoidally with time. All right. So because it's a perpetual motion machine, it's going to be sinusoidal. It's going to be constantly between 60 and 40. The rider sets the spring in motion by compressing it to its high point of 60 centimeters and letting it go. At which time he starts his stopwatch. Okay? So he's learned his lesson. So there's a couple of ways to start this, right? You could pull it down to 40 and let it go. Or you can push it up to its high point and compress the spring and let it go. He chose to compress it to let it go. So up here at the high point, that corresponds now with t equals 0. All right? Now it tells us 1.8 seconds later, it gets its closest to the floor, 40 centimeters above it. So less than 2 seconds later, it's down on the bottom. Part A, sketch the graph of the sinusoidal function. All right, will do. So there is a y-axis, and here is a t-axis, actually, or x-axis. And we're going to be measuring the height again, h of t above the floor, but not in feet this time, in what? The guy's using centimeters, yeah. Okay, and we're measuring time on the x-axis in what? Seconds? Seconds? Yeah. Okay, so again, we can, like in the previous example, it's kind of nice. We can let the x-axis kind of act like the floor because we're measuring the height above ground. And so the low point was, let's just do this. We'll kind of like have a break in the graph right there. This is 40. We'll come up there and make that 60. So you notice the 40 from the x-axis is not really to scale compared with the 60. That's fine. If you want to put this little hash mark right here, that just means like we're breaking it and bringing it down. If you don't have that, I won't even count off, okay? But it is kind of nice to have that. So from a low point to 40, high point to 60 then, what would be the midpoint? 50, right? You can go 60 plus 40 is 100 and divide by 2. Or you could just say, oh, halfway between 60 and 40 is 50. What's the significance of 50 in this problem? Good, it's the central axis. Also known as the sinusoidal axis. I don't care which one you call it. Sinusoidal central axis. Every time I say sinusoidal, I think of Curly Howard from the Three Stooges. Did you ever watch him? He's the guy, the funny one that went soidally. So I'm thinking like sinusoidally. That's just me, though. I shared it with you. Yeah, thank you. Okay, so we have the vertical axis, and now remember the fun part is always the x-axis or the t-axis. So again, this one's kind of easy because it says at t equals 0, he starts it at a high point. So that starts with t equals 0. Now 1.8 seconds later, I'm going to come out arbitrarily right here. It's at a low point. Now why did I draw the low point so far away from the y-axis? Well, because from a high point to a low point is what fraction of a cycle? Is it a quarter? Full cycle? Half cycle? It's a half cycle. Good. So that would be the half cycle. So I'm going to need another number in between there. But this is, I can label that one as 1.8. All right. So now let's bisect that. Half of 1.8 is what? You have $1.80 and I take half of it. I leave you with what? 90 cents. Good. Okay. You must have had like a bunch of dimes and stuff for me to be able to take that. And now we have our quarter cycle counting interval, right? From 0 to 0.9 is our quarter cycle counting interval. So now I can just kind of keep the distance the same and put a couple more marks out there. I'm not going to get so crazy. I'm just going to do that. All right, so you want to put the dots first or label the x-axis first? Label? Okay, yeah, we always put the dots first. Let's let the dots wait this time. Hold your horses, dots. Let's count by 0.9. 0.9, 1.8. What's next? 2.7. 3.6. Yeah, it's just your multiples of 9, right? And then 4.5. Good. So on and so forth with the decimal. Your factors of 9 with the decimal. All right, now let's put the point. So we know that at 0.9 it should be on an axis. 2.7 should be back on an axis. 3.6 should be up high again. Thank you. And 4.5 should be back on an axis. Good morning. Okay, now let's go ahead and draw it. By the way, do we want to draw any in negative land here? No, our relevant domain, again, remember, is t has to be greater than or equal to 0. Negative values don't really make sense here. Now on example 2, it did. If we wanted to start 12 feet in the air, we could have had a negative value and extrapolated backwards to see where he was. But in this case, it's greater than 0. And now we connect the dots with our smooth curves, right? And remember, the central axis is also the sinusoid, the inflection point. So that's where you want to kind of go from what we say concave up, like a cup, to concave down, like a frown, like a parabola up, parabola down. Okay, and that's good. We turn the corner, and it would keep going if we wanted to. So we'll put an arrow. All right, so there it is. That was pretty easy. And I've got the axis labeled, right? The height in centimeters, time in seconds. Okay, so that's part A. Part B now. Find the particular equation in centimeters as a function of time. So h of t equals, that's our first thing. Let's see if we could do this without listing the A, B, C, and D. Let's just see if we can get it from the graph. We need A first. What's A going to be? 10, right? From 50 to 60 or from 50 to 40? That distance is 10. I'm going to leave a little space in case I want to go negative. You want to do sine or cosine? You'll flip a coin. Sine or cosine? Sine. Okay. So was that heads or tails? It was in the middle. It was in the middle. Okay. So let's do sine. Do you want to do a positive or negative sign? Positive. Okay, good. I'm going to scooch my 10 closer to the equal sign then, since we don't need the negative. And I like your attitude there. So positive. So positive sign. Parentheses. What comes next? The period? No. B. How do we get B? Do we get B directly from the graph? No. B is the number of cycles in 2 pi. We don't even have 2 pi graphed there. That'd be 6.28. I wouldn't be able to figure that out exactly. So remember, from the graph we get the period, and then we convert it to a B value. What is the period? You call it wavelength in science, right? It's probably easier to measure from crest to crest or trough to trough. So from 0 to a high point, where's the next high point? 3.6, yeah. 3.6 seconds. All right, so now the B value, that's going to be 2 pi over 3.6. Now look at that. Yucky, yucky, gross, gross. That is mixed notation. That's like talking to someone in English and Greek in the same sentence. Why would you do that? Right? We have 2 different representations for parts of numbers. Fractions and decimals. Pick one and go with it, bro. Well, I don't want to go decimals because the pi is there. It's irrational. I'd be going on forever. And then if I stopped, it wouldn't be exact. So let's convert 3.6, or we can simplify first. If I divide out the 2, what's half of 3.6? 1.8. That's still yucky, yucky, gross, gross, but it's better, better, gross, gross. So let's convert 1.8. Ooh, that's a long pi. Let's convert 1.8 to a fraction. That's the same as 1, and let's do it off to the side here. Remember little school? That's the same as 1 and 8/10, right? As a mixed number. Well, that's the same as 1 and 4/5, right? As a mixed number. And you remember how you did that? You multiplied and added? Or you can just call 1 5/5. That's 5 plus 4, that's 9/5. There we go. 9/5. That was fun. Little school on the side there. Now that's still yucky, yucky, gross, gross, because now we have a compound, complex fraction. So dividing by 9/5 is the same as multiplying by 5/9. Good. And 5/9 times pi is 5 pi 9. Oh my gosh, that is beautiful. 5 pi 9 compared to 2 pi over 3.6? Yes, please. Yes, please. Okay. If this were a multiple choice question, that would be the b value that I would have. So anyway, there you go. Converting decimals to mixed fractions. So I'm going to put 5 pi 9 right there. That's my b value. Okay, now we chose positive signs. So we're looking for a spot on the graph where we are where? Axis going up. If you want positive sign, it's axis going up. Sign always starts on the axis. Positive is always up or going up. So where are we on the axis going up? 2.7. So I got to shift over there. T with a 2.7. Is it going to be plus or minus? Minus. Good. It's always the opposite sign from on the number line. And then I just add my d value, which is 50. There you go. That looks like it should work, right? Now I'm going to ask you questions about that equation. I'm going to ask you again, where's the height at a certain time, or at what time is it at a certain height? So before we use that, we better check it, right? We have a beautifully sketched function right here in a certain window. We should check our equation to make sure in this window it matches up, okay? So let's do that. We go to y equals, and we're in radian mode, so 10 sine of, if you want to do alpha y equals, that's great. 5 pi 9, that's pretty, times, we use x again, x minus 2.7. Close it for the shift, close it for the angle, plus 50. Okay? Now we go to the window, and we look at the window that we've created, and we match it up, okay? Match up your window. I'm going to go from -1 again, because I like to see the y-axis. We went out to 4.5. I'm going to go out to about 5, just a little bit further. X scale doesn't matter. If you want to put it at 0.9, because that was our scale, you can. You can leave it at 1. You can put it at 0. Y min, I'm going to leave it at -1, because I like to see the x-axis. And what would be an appropriate y max here? 60 is our high point, but remember, we like a little buffer. 70, 65, yeah, whatever. There's really no wrong answer there. Just don't go to like 7,000. Otherwise, you're not going to see your graph. Y scale, 0, 1, it doesn't matter. I like to put it at 0. Okay, so here we go. Does that look like our graph? For the most part, yeah. Now let's verify, remember. Let's hit trace, and let's pick one of our numbers like, oh, I don't know, 3.6, right? 3.6 should be a high point. 3.6, after I hit trace, it's up there at 60, like I want. Let me do one more. 4.5 should be in the middle going down. And yeah, it appears so. If you want to verify that, remember, you can graph your central axis just by putting 50 there, and you'll see that it goes through there. And now you could do trace 4.5 if you want, and you'll see it's right there on the line. Okay. In general, we don't need to graph our central axis, so I'm going to get rid of that. So is our equation correct? Yes, it is. All right. Now, let's do one last thing here today. Let's go ahead, and I hate to end on a negative note, but maybe I'll just say one more negative thing to you on the way out, right? And 2 negatives make a positive. Let's do a negative cosine. -10 cosine of 5 pi 9, parentheses, t plus or minus something plus 50, right? Everything's going to be the same. Your amplitude is still 10, b is still 5 pi 9, and d is 50. We just have a negative a value now in cosine. And what are we looking for on the graph for a negative cosine? A low point, right? Cosine always starts on the extremes, high or low. Negative is always low or going low. So I need to shift over to 1.8. So x minus 1.8. And one last thing then, if I put minus 1.8, I'm just going to type this in one more time and verify. Negative cosine. Oops, sorry, negative 10 cosine. That wouldn't work. Negative 10 cosine of 5 pi ninths. You could type it in like this if you want. 5 pi ninths. My calculator just froze. Great. Great. Right here at the end. Stupid calculator. There's one more negative thing. I'll throw it at my calculator instead of y'all. Anyway, if you type it in and hit enter, what should happen? Nothing. If you have a black screen, you won't see anything. Mine would have traced the red graph directly over the blue graph. Okay, we know we're right. We know we're awesome. We're better than the stupid calculator. Okay, tomorrow we'll finish this section pretty easily. And Wednesday we'll review. You should always walk in ready for a quiz and disappointed when we don't have one, right? Especially like a unit circle quiz. You should always just be ready for one. Like a 4-minute quiz or something on the unit circle. Just you should always be ready. No. To like 10, like we done, like all the using the unit circle, little strips of paper ones. Yeah, that just means don't forget the unit circle. We've worked hard to memorize it. Don't forget it. Okay. Have a fabulous day.